Okay, now I will continue with the slide number 23, okay, on the fourth step, which is the soft baking. Okay, what is the function of soft bake? Okay, it is to remove the solvents, okay, from the photoresist, okay, so this will make the photoresist will be much more sturdier, okay, and then here we shall activate the photoactive substances, photoactive compound that is available in the photoresist. Okay, and then another point that we can add in, okay, is the we would like to remove the stress in the photoresist, okay, due to the solvent, okay, and then we shall improve the photoresist addition. So this is the reason why we have a soft baking in this process. Among the parameters that we should consider, okay, while doing the soft bake, the type of heat transfer, okay, either we are going to use the hot plate or through oven, okay, using convection, and then we need to make sure what type of temperature that we are going to use, okay, and then the temperature uniformity, okay, how long should we do the soft baking, okay, the exhaust, and also the cool down rate. So I won't expect you to remember all the parameters, okay, but if in the future you would continue to do your masters, okay, or you want to do start some study in microfabrication that use this photoresist technique, okay, use the photolithography technique, okay, so these are the parameters if you want to optimize your soft baking. Okay, next step, okay, is the alignment and exposure of the silicon wafer, okay, with a layer of photoresist on its top, okay, and the silicon wafer with the photoresist will be aligned to the mask and then exposed to the UV light. So this process is important because you will create the pattern, onto the wafer together with the photoresist. Okay, in slide 24, okay, you can see the position, how do we position the UV lights, okay, the mask and the lens, okay, and also the wafer. So you know how do we form, okay, how and what is the step that is involved, okay, to make the pattern, okay. So with this technique, okay, you will have the pattern transferred onto the wafer. Okay, for the slide 25, this is the description of a mask, or known also as the photo mask. Okay, the photo mask is the master copy for the pattern. It's the master copy for the pattern for the wafer. Okay, so actually for our study, maybe we just show you one example for this, okay, but then actually for a typical chip, okay, for a complex chip, it can be actually sometimes even thousands actually. Okay, in our slide we just say about 50, but actually yes, maybe the latest, I'm not sure how much, but then for the 1999 chips, okay, it can be up to 1000. Okay, so actually there's a lot of masks, okay, there's actually a lot of masks involved in one microfabrication work. Okay, so okay, one of the most important part, okay, for this slide is that, okay, the substrate, okay, here the substrate is not the silicon wafer, okay, this here the substrate means the mask, okay, the substrate for the mask, or usually known as a blank, okay, is made from some form of glass. It can be made from a normal glass. Okay, we will go to that topic after this. Okay, so you have to remember that the blank here, the substrate here for the photo mask is called blank, okay, and then this blank is made from some sort of a glass. Okay, so how do you have the pattern? Okay, the pattern is made, okay, by, okay, there's a chromium layer, okay, on one side of the glass, which acts like a light barrier. So this light barrier that will form the pattern. Okay, to make the pattern, the chromium layer, okay, the chromium layer is selectively removed to form the openings for the light to create the pattern. Okay, and surprisingly, okay, not actually so surprising, but we can say that the patterns created using photolithography itself. Okay, but okay, and you can, okay, the other name for the mask is, okay, apart from photomask, is reticle. So I would like to summarize for this one slide. Okay, first of all, you need to know that, okay, the photomask, the substrate, okay, the substrate for the photomask is called blank, and this blank is usually made from a glass. Okay, and how do you make the pattern? Okay, the pattern is made by a chromium layer. Okay, you have one chromium layer on one side of the glass, okay, and this chromium layer act like a light barrier, and then the pattern, okay, the pattern is made by a selectively remove the chrome, okay, to form the openings for the light. So you need to know this by heart. Okay, these 2 points by heart. Okay, for the slides 26, okay, the slide is about the characteristic of a mask. Okay, so what are the things that should be abide, okay, by the mask. Okay, and there's 4 points there. Okay, I know point number 1 and point number 3 is a bit lengthy. Okay, but if you understand, okay, if you read the slide and also refer to this voice note, okay, I think you can understand this better. Okay, first of all, okay, a good mask, okay, a good characteristic of a mask should have no defects. Okay, no defects. If you answer no defects, that will be good. Okay, that you can have your full marks. Okay, so then there's the explanation of it. Okay, no defects should be allowed. Okay, the defect is catastrophic. Okay, like if you refer to our earlier slide, okay, showing a hair on top of a chip, so it has the same, this is the same idea. Okay, if you have a defect, okay, every time when you do your photolithography, okay, for every time you have the exposure, you will repeat the same defect. Okay, so the materials, okay, and also the process, okay, while you're doing the procedure of while you're doing your photolithography, must be defect free. So on your mask, okay, it should be perfect. Okay, you any what we call the structure that you required should be at the same, what I call size, okay, size and everything. Okay, and if there's a defect, okay, you should discuss it with the vendor. Okay, that's the first point. The first point, no defects. Okay, no defects at all for your mask. Okay, the second one is the high transmission. Okay, how to remember it is easy. Okay, the mask, it should let in the light. Okay, so the intensity of the light, okay, exiting from the mask should be nearly equal to the intensity of the light entering it. So whatever the light comes in, okay, should be the same when it comes out. Okay, you don't want it to like a hindrance to the light. Okay, so it must be high transmission. Okay, the best transmission that you can get. So this, why? Because okay, if let's say it has a low transmission, it will affect your photoresist. Okay, as you remember, both photoresist really depends on the lighting. Okay, if there's any problem of the lighting, then okay, your mask is no good. Okay, the other point is the edge resistance. Okay, both the substrate and light barrier must be resistant to environmental chemical attack. So you have to remember, when you do your photolithography, okay, your work is exposed to many types of chemicals and so on. So okay, while you are cleaning, maybe while you're doing your work and everything, so you have to make sure that okay, your blank, okay, your blank must be resistance to chemical. If you answer it as a chemical resistance, you get your full marks. Okay, no problem with that. Okay, so okay, so the standard answer should be like edge resistant, but if you put chemical resistant, that will be okay. Okay, so while you're cleaning the mask, okay, the chemical will not harm the mask. Okay, but you still can remove. Maybe you have some like photoresist, okay, on the mask. Okay, maybe you have that. Okay, but yeah, and while you're cleaning it, it won't affect your mask. Okay, the last one is a low thermal expansion. The last point is a low thermal expansion. So okay, it's easy here. Okay, you have to remember that you are exposing the mask, okay, to the light. Okay, when you expose, okay, the mask to the light, it should, okay, logically it will heat up your mask, okay, your glass mask. So okay, so in the end of the day, your mask will expand. Okay, so it should have, your mask should be not that sensitive. Okay, it should have a low thermal expansion. So okay, and this low thermal expansion, okay, your pattern also will not be what I call influence. Okay, will not be influenced with the heat and so on. So you have your actually, okay, if let's say your structure is like 5 microns, it will be 5 microns. It doesn't not due to the light. Okay, not due to the light, the heat comes from the light. Okay, it will become like 6 microns and so on. So there are 4 points. Okay, 4 points which define a good mask. Okay, first of all, no defects, then the higher transmission, then you have the edge resistance, and last is the low thermal expansion. Okay, for slide number 27. Okay, here we talk about the type of materials that we are using to make the mask. Okay, the mask blank. Okay, so basically it is made from glass. Okay, there are 4 types of glasses that we are using here, which are, the first one is the soda lime, then the borosilicate, the quartz, and also the last one is a fused silica. Okay, you need to know the characteristics for all these classes. Okay, the characteristics for all these classes. The easiest one is about the cost. Okay, if let's say you don't remember, okay, please remember about the cost. Okay, so soda lime. Okay, soda lime is the cheapest of all. Okay, it's the cheapest of all. Okay, but you just use it for large geometry. Okay, large patterns. Okay, or some like worker that has a wide registration specs. Okay, so it has run out, okay, of 0.24 micrometers per degree Celsius, okay, per inch of substrate diameter during e-beam writing. So means that, okay, this will cause some like expansion. So it has a higher thermal expansion compared to other type of glasses. Okay, so here the point is that, okay, soda lime, what type of application that you can use. Okay, first of all, maybe you just want to have a test. Okay, you don't need a very high cost mask, something cheap. Okay, and then the pattern is big. Okay, the pattern is big, and then if let's say you are your pattern is not really affected by the run out, okay, so that will be okay. Okay, another type of glass that you can use is the borosilicate. Okay, it's moderate, okay, not that expensive, but it's seldom used. Why? Because it has a 1/3 of the run out problems. Okay, and the disadvantage, okay, disadvantage, it has a lesser transmission than soda lime. So not what we call the transmission is not as good as the soda lime. Okay, so you can okay, you have to think how what type of application you can use for borosilicate. Okay, maybe something that is not very affected, okay, by the transmission of light. Okay, so the third type of blank material you can use is the quartz. Okay, this usually used in the industry. Okay, it's a industrial standard for high precision registration. So means that, okay, you can use it for smaller pattern. Okay, smaller patterns. Okay, this type of blank material, okay, this glass has a excellent transmission. Okay, even with lower wavelength, 248 nanometers, and then it has a low run out by a factor of 20. So this is very good. It's not going to expand bigger. It's not going to expand larger compared to the soda lime. Okay, the last one is the fused silica. Okay, necessary for 248 nanometer extended lithography and 193 nanometer nodes. Okay, quartz is too birefringent. Okay, birefringent is that it is very sensitive to the polarization of the light. Okay, but okay, so if your application very sensitive to the polarization of light, fused silica will be the option. However, like soda lime, it has a problem of thermal expansion, so you have to be careful of it. So you have to balance between the birefringent problem and also the thermal expansion. Okay, for the 28th slide, okay, it's about the light barrier material. Okay, this light barrier material will form our pattern. Okay, so it is usually made from chromium. Okay, and the thickness is around 600 angstrom to 1000 angstrom thick. It is 600 nanometers. Okay, it's 60 nanometers to 100 nanometers thick. Okay, so you have to check the what we call the unit that you are going to use. Okay, so it is placed on one side of the glass, and then and then we apply an reflective coating of 20 nanometers or 200 angstrom. Okay, also it's made from chromium oxide. Okay, to make sure that it is not reflective. Okay, so for your mask, you have two sides of it. Okay, first the chromium size. Okay, the side of the mask will face the wafer. Okay, this is during the exposure. Okay, during the exposure process. Okay, the side of the mask, okay, that have the chromium side will face the wafer, and the glass side, okay, the side of the mask facing the light source. Okay, so this is how you organize your mask. Okay, for slide number 29, you have the pellicle. Pellicle is just a sheet that protect your chrome side, of the mask. Okay, so the pellicles throws contamination out of focus by keeping it several millimeters away from the chrome side of the mask. Okay, however, the disadvantage is that the little light is lost through a pellicle. Okay, it is usually made from nitrocellulose or mylar, and large particles will still cause transmission defects. Okay, it is usually good for projection liners. Okay. Pellicles is very susceptible to attack from solvents, okay, because it's a polymer. It can easily damage, okay, it can easily damage, and sometimes, okay, you have problems in terms of it's expensive to replace them. So these are the things about the pellicles, Okay, so for the slide 30, okay, you have the post-exposure bake. Okay, so what are the function of this post-exposure bake? Okay, to reduce the effect of standing waves again. Okay, to reduce the effect of standing waves which occur during exposure, and then to increase the resistance of the resist prior to the etching process. So from here you can see the what I call it tips for the post-exposure bake. Okay, here you can see that all this baking, okay, if let's say you cannot remember, first of all you make it you make your photoresist stronger, actually, okay, stronger, and then you want to reduce the effect of standing waves. So these are the okay, if any of the baking is something to do with that, if you can't remember, okay, and like all other baking, okay, you need to consider type of plate, temperature, uniformity, time, okay, cool down rate. You have to consider all those parameters. But like I told you, okay, the parameters, okay, you don't have to remember it, okay, but please, okay, please have put some effort to remember, especially on the temperature and time. Okay, now is the slide 31, okay, for the development process. This is an interesting process. Now you can see the pattern of interest that you are working on. Okay, so what is the development process? We can say it is to remove the area of resist that have been exposed or unexposed, okay, to form a pattern. So being unexposed is due to the type of photoresist you are using. Okay, and another point is that, okay, development rate for positive resist is much less than negative resist, so it will be much faster. Okay, so if you are dipping a chip or a wafer with positive photoresist in a developer, it will be faster. Maybe, for instance, okay, maybe for negative photoresist, it may takes like 10 seconds, okay, but for the positive, it may takes around 7 seconds, okay. And there's a list of the parameters you should watch out, okay. Development technique, okay, developer type, developer concentration, developer temperature, development time. Usually for novice, okay, for a novice, development time is important parameter, yeah. Okay, the resist thickness, okay, the post exposure big temperature you are using, the exposure energy. So if the energy is more, okay, it will be faster. So these are the points that maybe you don't have to memorize all the parameters, okay, but make sure that you know a few points, okay, maybe a few points will be good. Okay, for slide 32, okay, we still talk about the development. Okay, here what happened, the developer solvent dissolve the softened part of the photoresist, okay, and here we transfer the pattern from the mask or reticle to the photoresist. Okay, so for this development process, you have 3 basic steps, which is the development, which means that you dip, okay, you dip your chip or your wafer, okay, together with your photoresist, okay, into the developer. Okay, take it out after you notice that you have your pattern of interest. Okay, then you rinse it. Okay, you rinse with the ionized water. Okay, and then you dry it. You blow it with a nitrogen air. Okay, for slide 33, this is interesting. Okay, we talk about the developer solution. okay, what type of solution that you're going to use. You are going to use. Okay, so what happened is that the soluble areas of the photoresist are dissolved by developer solutions, which are usually made by a wick-based solution. Okay, so one type of developer, okay, this is just one example, which is a timah, okay, timah tetramethyl ammonium hydride. Okay, this is one type of the solution. It doesn't have to be this one, but okay, just to make just as an example, okay, for you. Okay, so timah will be used. If you write TMAH, okay, in your answer script, okay, you get your full marks. Okay, no problem. Okay, so after you have developed it, you develop your wafer or your chip. Okay, you will see your pattern. Okay, and then you have to make sure, okay, while doing development, okay, while dipping your sample, okay, the line resolution is good, okay, it is uniform, and then it doesn't have any particles and defects. Okay. For slide number 34, okay, we'll talk about the hard bake. This is the last, okay, of the baking after the development process. Okay, in this section, okay, what is the function of hard baking? Okay, here you will like to increase the resistance of the resist, and then to remove any residual solvent. So first of all, this is the final baking. Okay, the final baking, so the resist will be very strong, okay, in this process. Okay, and then it will, okay, so if there's some more solvent, it will be removed. Okay, and just like other baking, okay, baking process, you need to consider type of plate, the temperature uniformity, time, exhaust, and cool down rate. Okay, let's say in the end of the day you are not satisfied with your pattern. Okay, you feel that you need to redo again the photolithography process. Okay, there's one solution which is called stripping. So you strip, you remove your photoresist, and then you start all over again. So stripping, how do you do stripping? It's easy. Okay, you just use certain type of chemicals, usually acetone. This will remove your positive photoresist, and for the negative photoresist, you use methyl ethyl ketone. So with slide number 34, it is the end of the process of photolithography. Okay, so for slide number 35 until 37, we will talk about the key quality issues of lithography. Okay, so for slide 35, okay, there's actually 5 issues regarding to photolithography, which are the exposure energy dose, okay, whether, okay, it is under or over development, okay, alignment of the photolithography mask with features on the wafer, okay, the resolution, okay, the smallest feature size available for a given lithography process. The other one is depth of focus, range of focus settings that provide solution at the same exposure energy. Okay, contrast, okay, ability of a resist to produce acceptably sharp images. So there are 5 of it. Okay, and this will be touched in details in the other 2 slides. For slide number 36, there are 2 issues here. Okay, the first of all is about the exposure energy dose. Okay, for a given exposure system, okay, the issue is that the dose is either too much or too little, depends on the exposure time. So let's say if you put it under like a less exposure, which is underexposed, so you have a larger pattern. Okay, if you compare to the desired pattern. Okay, please refer to the underexposed pattern. So let's say you are overexposed. Okay, you are overexposed. You can see that the pattern is smaller. It's like being eaten up. it is smaller, so you don't have like a perfect square. Okay, you don't have the perfect square as the one that you need. It is smaller than the desired pattern. And for the underexposed, okay, you have a bigger square. Okay, bigger square, bigger rectangle, because it is not it is underexposed. Okay, and then there's an issue of under or overdevelopment. If you are overdeveloped, okay, you will also have the same pattern like the overexposed. Okay, if you are underdeveloped, you will have a pattern similar to underexposed. Okay, so these are the issue that you have to consider, okay, during the exposure and also during the development. Okay, for the slide number 37, this slide will be the final slide for the photolithography issues. Okay, and this one, okay, shows that the importance of to make sure that the alignment is done well. Okay, because usually we are not just working with one type of patterns. We sometimes we have like 2 or 3 type of patterns that we are going to work with. So you have to make sure that that the pattern is aligned well. Okay, so usually you have these alignment marks. Okay, you can see, please refer to the cross. The cross, the small cross should be in alignment with the bigger cross. Okay, so that you have a good what we call alignment between 2 type of patterns. Okay, so the alignment marks used to register 2 levels. Okay, and if it is correctly put, okay, now the wafer is ready to be exposed. Okay, for the next lecture, okay, for the next lecture, we will cover the soft lithography. But okay, for now, we end our lecture for the time being. Okay, until slide 37. Okay, thank you very much.